Thank you. No, don't do that. People fall asleep. It's deadly. Much better to have the light on.
Yeah?
Okay, I guess I can ask for popular desires. I think the lights on is better than off. On. Okay, that's my choice. Okay, so I'm going to talk about the network formation model. And this is joint work with Larry Bloom, David Isley, John Kleinberg, and Bobby Kleinberg. And I guess the main feature of this slide is the contagious risk. And let me try to tell you where I'm coming from as the beginning. Okay. So there are a lot of network formation models out there, or network formation games and network formation models of all sorts. I guess basically in classes that either strategic or probabilistic models. They're trying to explain to you networks of the form that you see over there, the recommendation networks, email networks, all kinds of other networks in, I guess, to give you a little sense, probabilistic models usually come with either sort of preferential attachment. They sort of try to give you a probability that you're going to join some other node. And I guess, maybe recommendation systems work like this, that in order for you to have a relation with someone, the people who are very connected are sort of higher value and connect to that. Or people study small word networks where the probability has to do with some sort of physical distance that decays in distance. I guess mostly maybe John Kleinberg. I guess the first one is maybe highlighted by Barabash's work, and the second maybe in John Kleinberg's work. There is a lot of strategic network formation also, maybe prominently beginning Jackson-Walensky's paper, where usually people strategically agree to form networks, and that, again, it's sort of trying to model the same thing. You have benefits from having been connected to a lot of people because they send you job suggestions, recommendations, whatnot. The models sort of look like this, and I guess you don't have to read the exact formula here, but basic idea is that if you're this node here, you make some decisions about forming links, and links have some cost to you. You're going to have to maintain friendships or do something to keep the other guy happy. That has a cost, say in a simple model, a fixed alpha, and you get benefits from being connected to a lot of people. Maybe the Jackson-Walensky model has a parameter delta, and this benefit decays exponentially with distance. So your benefit is delta to the distance to whoever you're connected to. What we're going to do in this work is actually reverse this whole trade-off function. So it's going to think about the strategic model, but going to completely reverse of which way the benefits and trade-offs were. So the standard model had costs for the link. You had to maintain the relationships, but there are some good things that were reaching you from far away in the networks, like recommendations coming or suggestions coming. In our model, it will be backwards. The benefit will directly come from the link, and instead some bad thing will come from far away, some danger that you don't want to get exposed to. So being connected to a lot of people will be negative, a bad thing, and being from far away, being connected to them in a single one-hop pass possibly is a good thing because it has a direct benefit. So to get you a sense of what am I thinking of, there are a lot of applications where the dynamic is like this and not like the traditional dynamic. So I guess one motivation might be financial networks. So say the picture here apparently is the network of overnight loans of some set of banks, or large set of banks. I guess if you think about this, the overnight loans for a bank, the banks loan each other overnight something because there's a direct benefit. They get some sort of reward for having loaned money. So there's a direct, immediate benefit for forming an edge. And what's the danger? The danger is that someone might default and not return the money. And in fact, it's not, I mean, if you lend someone money, there's the direct danger that the guy you lend money defaulted and doesn't return the money. But it's worse than that, because if you loan someone and then he loans someone else and that guy defaults, then might indirectly cause your guy to default also and then not return your money. So in a way, this is a contagious risk. That is, if someone far away defaults, there's some probability that that thing will spread to you, because then his neighbors default, and then eventually your neighbor defaulted, and you're in trouble. So there is some risk of that. Similar models actually have been used explicitly in thinking of epidemics or disease spreading. And I guess maybe the context which has been explicitly looked at is HIV needle sharing, or actually also maybe sexual behavior, but there's studies on, there's evidence to suggest that once HIV became well-known, AIDS became a risk that people explicitly thought about, they did change their behavior. That is, needle sharing or sexual contact has an immediate reward, but it exposes you to AIDS. And apparently, according to these papers, when people became aware of the danger they're getting exposed to, they decreased the amount of links they form or decreased the size of the components. That is, they reacted to this danger coming from far away. If you share a needle, you might get AIDS, or if you share a needle in a chain of needles, there is some chance that you get infected with AIDS, which is some really bad thing, similar to having your the partner you loan money to defaulted. I guess similar things happen in sort of secret organizations of some sort. Links are obviously useful. That's how you coordinate. But if your neighbor got exposed, then maybe you can get there's a chance that you will get exposed also. Okay, so this is motivation. Now, with all this motivation, I guess we're going to use a pretty simple model. And let me tell you what our model is. Players are going to, there's a set of V of players, and we're going to believe that there is an absolute upper bound, a large constant. So the number of players will go to infinity, or think of large graphs. They're going to be a large delta, which is the maximum number of relations any human can manage to have. So there's an absolute degree, and there's a benefit A, a large benefit A, for forming such a relationship. So if you have degree delta, then you have delta times A benefit. Under this, I'm going to allow people to form a network, and then I'm going to expose them to a failure process. And here is what, and I apologize for this being a little low here, but I'm going to read it anyhow. So the failure process goes as follows. There is spontaneous. At the moment, I'm using two parameters. Some probability Q independently, every node will fail. Think of Q as very small. So a few nodes will fail. And then with another probability, also very small, P, that will spread on every edge. Again, edges independently. So if your neighbor is infected or failed, whichever analogs you think of better, then there's a probability P that along the edge it will spread to you. Oh, I'm really sorry. This thing is a P here. I'm sorry. Yeah, I'm hoping that the future slides will always have it as a P. So that's a Q and that's a P. Sometimes in the slides I will take the special case of a simplicity of P equals Q, and then I'm going to be okay. But for now, it's supposed to be Q and that's supposed to be P. Okay, and what you're supposed to think of is, again, it's very similar to the model that was used by Jackson and Volinsky backwards. That probability of infecting you decays exponentially with the length of the paths, except I have a multiplier on it with a different number of paths. Like if there are many paths, then it sort of adds up. Every edge independently carries the infection with probability P. So if there are many paths connecting you and the infected node, then your probability is higher that you get infected. So that's a model. Now, so this is sort of how it works. There are some number of things get infected. This is the maybe independently with probability P, and then we figure out which of the edges carry the infection, and the infection carries over to multiple nodes. Now all of the nodes failed. In order to finish this, I'm going to have to give you one more parameter, and that's on the bottom line of the slide. What happens to your objective when you fail? So if you fail, then A, you lose all the benefits you had from the links because you failed, you went out of business. And in addition, I'm going to slap you with an additional big loss B. Okay, I'm making you lose your benefits from the link. So no matter how many links you had, you never want to fail. That's always a negative thing. And then I want to make it worse than that. It didn't just lose the benefit, but there's an extra loss, B, which I think you should think as bigger than A. And I guess what I'm going to ask you to think of, that everything is sort of small and big here in the appropriate way, but everything is constant except the number of nodes. And I'm going to be interested of how this scales as the number of nodes gets bigger. So we're talking about the large constant degree that I'm allowing is a large constant delta, small probabilities P and Q still constant, A, B are constant, some rewards. But the only thing I'm driving to infinity is the number of the nodes, and I'm interested in what happens in large networks with these kind of parameters. So technically, the payoff is a little awkward to write, but maybe is interesting. It is worth formulating. In order to figure out the payoff, there's the part of the payoff that has to do with failing, and I'm going to have to figure out, and we know this is sort of a non-trivial exercise to figure out what is the probability that a node failed, because it has to do with what it spreads. But for now, I'm just going to call it phi of A is the probability that node A failed, and then this is technically the payoff for a function. It had an A benefit for each of its neighboring edges, so degree of A. He had this with probability 1 minus phi, because in case it failed, it lost that benefit. And in case it failed, it also lost an extra B benefit, an additional B penalty for having failed. That's the payoff function for a node. Now, I have to tell you one more thing, and then the model is really done. How am I evaluating the outcome? And I guess the paper or our work evaluates the outcome via this mean welfare that is the worst of node. Okay, the two natural objective function here is the average welfare and the minimum welfare. The minimum welfare seemed like a fairer measurement. If you look at average welfare, some unfortunate things happen in the socially optimal solution. We sacrifice some people in order for others to have big rewards, which somehow seemed like an unfair comparison. So we're evaluating the networks via the worst person, how badly off is the worst person. So we're going to look at two different issues, one that you should expect given the topic of the workshop and the setup here. I'm going to ask what the difference between a socially optimal network and a selfish network is, that is a stable network. And I'm going to ask a second question, which I think also has a very interesting answer, that the socially optimal network, under what allowances or how do you allow to form networks? So some transactions in life, or some financial transactions in life, say, go under the model that you approach, Sergio and say, Sergio, I want to do a transaction with you, and Sergio may or may not agree to do this transaction, but other transactions go in a sort of anonymous way, that I submit my desire to do a transaction and some anonymous system matches me with someone who wants to do that transaction. The second model, I don't control so finely. I can control my degree. I can put in how many transactions I want to do, but I don't control my neighbors. I cannot control my neighbors as carefully. We're going to call this anonymous model. And so I'm going to do two versions of the socially optimal solution, version when you're allowed to control your neighbors and version when you're not, and interested in the difference of what happens to social welfare, or our measure of social welfare, as you're allowed to control your neighbors more or less. Okay, I don't know why I'm doing this. That's a mistake. Okay, parameter ranges. So I told you that every parameter here, except for the number of nodes, is a constant. And I kind of have to figure out what are interesting ranges of constants. So I'm interested in small probability of failure. That's not because of a mathematical reason, but instead that's sort of if you talk about failure of banks or contagious diseases, those are not high probability events. So the interesting ranges when those probabilities are small. For the payoffs, I'm more motivated to get an interesting model, and maybe those are reasonable payoffs. And there's three things I'm going to assume. So I'm going to assume that if you are faced with the option of, in a single no networks around, you're person A, and there's a person B not connected to anyone, and you know nothing about either you or the link, you're going to want to form an edge with them. Okay, so what's your exposure or danger is P times Q, that is both your neighbor has to fail and the edge has to carry the infection in order for this to be bad for you, and then you'll carry a penalty, roughly speaking, of B, and your reward is A, directly A for forming the link, and A has to be bigger than B times P times Q, because otherwise the answer is obvious. No one's going to form any links. This is the nicest scenario for forming links. If you don't even form links under this scenario, it's not interesting. B is the the single penalty for failing. Yeah. Yeah, you lose your existing links too. You lose even worse than that. So I guess this is a sort of test scenario, and Sergio is catching me that I wasn't quite honest, because if you have multiple degrees, you can get, I could put an extra delta in here, you can get as big a benefit as delta times A, and this is still only your loss. I still think it's reasonable to assume that in order to make the model interesting, it better be the case that all in isolation you see a guy who's not exposed to danger, you're not known to expose to danger, you want to form a link to him. So that's assumption 1. Assumption 2 and 3, what happened here? Okay, assumption 2 and 3 will tell you scenarios under which you don't want to form a link. For example, if you know that your partner is infected, if I already knew that someone is infected and I still would want to form a link with them, seems like that doesn't lead to interesting model. Again, I'm slightly cheating. You might want to form a few of these and even still interesting, but I think the interesting range of parameters, if you know that your neighbor is infected or infected with incredibly high probability, you don't want to form a link. And similarly, the last one saying that if you know for some reason you knew that your link you're forming is going to carry the infection, then that would be a bad idea. This last one is least important for me. The first two are the important ones. You do form...
P and Q are not constant. They depend on the link.
Yeah, they're probabilities. No, in the model they don't. They're constant.
They are constant?
They're constant. That's going to be a nice question at the end, that this is a very uniform model and would be nice to do something that's not uniform. Good point. Sorry. Okay, and instead of assuming this, I'm going to assume that all these inequalities hold with a wide enough margin, so there's an extra parameter delta, and these inequalities I wrote them not only hold, but hold with an extra parameter, extra multiplier delta. They hold with wide enough margins. So this is the range of parameters that I'm going to be interested in. I'm going to show you some techniques, and I guess to start with, I can tell you what the main results are. So I guess I promised you 3 kinds of things, but for now, mushing them into 2 maybe is the good way to start. So the socially optimal, the trade-off between socially optimal and the selfishly formed networks. So socially optimal network, I claim that there's going to be that, which I'll show you in a minute, that A over P is some sort of natural trade-off, natural barrier. It's hard to go much above that, and that the optimal network goes just a little bit above that. And I'll tell you in a minute why A over P is so A was the benefit, P is the failure probability of the carrying probability of the edges, that 1 plus a little bit, where the little bit goes to 0 as delta goes to, as my separation parameter goes to 0. So the less I'm separated, roughly speaking, it's A over B. In contrast, selfish networks going to do incredibly badly. They have a similar expression with the 1 missing. That is, the welfare of a single node will be another function also going to 0 with the separation parameter times A over B. That is not, roughly speaking, A over B, but roughly speaking, 0. So selfish networks will have 0 benefit. In contrast, the socially optimal ones are a little bit above A over P. So before I tell you the other distinction about anonymous and this non-anonymous markets, or anonymous and non-anonymous way of forming network edges, let me also tell you a little bit about the techniques we're using, and I guess then maybe will lead to the second distinction. So one natural thing when you're faced with sort of a lot of random decision, that the interesting machinery in your hand to flip some coins before you're flipping other coins. And the coins I'm like flipping first is the edge coins, actually, sort of backwards from the way the model was set up. So what does it mean to flip the edge coin first? That I'm going to decide which edges failed independent, which edges carry the infection independently with probability p. I do that before I decided which nodes were infected. And that would mean that there is this what may be called live edge network. So every node belongs to a live edge component. Anyone in your component fails, that these edges will carry the infection to you. If no one in your component failed, they won't carry the edges to you. So what you're going to be interested after you form this live edge network is the size of your component. If your component is big, you're in trouble. Each of your nodes in your network has probability Q of getting infected. That's an awful big probability if your component is big. If your component is small, you're okay. You're unlikely to get infected. That's basic message here. So you're going to have to analyze a random subgraph of a graph. We know a lot about random graphs. Yeah, I already said this. So we know a lot about random graphs if the original graph is the complete graph, and I kind of remind you what's useful here and what's useful here about this. And what we need to do to get these results is to carry those results from random subgraph of the complete graph to random subgraph of an arbitrary graph. Okay, because the arbitrary graph, the selfishly formed graph, is not going to be complete. Now, what are the results that are useful for me from random graphs? From random graph series, so here's a complete graph, and I formed a random subset of the edges, and I'm interested in the maximum expected component size. What is the biggest components I'm going to have? Why am I interested in the biggest component? Because I declared the worst off person to be my objective function, and the guys in the big component are in trouble. The biggest components are the guys in the biggest trouble. They're going to have a large chance of getting infected. So what do we know about this? We know a pair of theorems that basically probability 1 over the size of 1 over the degree, 1 over the size, the n, that is the size of the network, is the critical probability. And if you are below that critical probability, then the probability that a node A is in a component of size c is exponentially decaying with c. That is, they're very small, very few, they're teeny components all over the place. There are no big components. In contrast, if you push the edge probability above 1 over n, which with some 1 plus x over n, for a fixed x, then there is a fixed probability that a constant size component will arise. Instead of reading the formulas, maybe best off reading the picture. This is the x, that is, your probability of edge formation is 1 plus minus x. This is the probability of edge formation, which then causes the expected number of edges. The critical expected number of edges is 1. If you expected more than 1 edges, you're likely to have a giant component, constant fraction of the nodes. If you have expected less than 1 edge per node, then you expected not to have a big component. Every component is small. Okay, and what's bad news for us if there's a big component, because the nodes in the big component get infected and have a large, have a large negative payoff. Okay, this is for complete graphs, yeah?
So the structure of the big component is also important, right?
No. So I'm pre-flipping which edges carry the infection. So the big component is in the subset of edges that carries infection. So technically what we need to do, and that's a sort of mathematically interesting part of what we're doing, is carry this to not the graph G not being the complete graph, but the graph G being an arbitrary graph. Step number 1, if I'm actually doing the sort of anonymous model, that is, you only describe your degree, you selfishly, possibly non-selfishly declare a degree, and then some edges fail at random, that's actually incredibly friendly. That's the easiest regime for me. Because then you did form a random graph. The live edge graph is a random graph. You first chose random neighbors, and then you choose a random subset. The two processes together is really a random graph. So then I actually can use this stuff exactly as is. The other two regimes is less friendly, because an optimal graph may or may not be the clique, and even worse, a selfishly formed graph is more surely not going to be a clique. So I'm going to have to figure out what can I say about this kind of result with an arbitrary graph. And there is a very natural extension sort of carrying a proof of the previous result due to CARP. And here is the version that I'm going to use. If I have a graph with large minimum degree, that is, every degree is relatively large, like as in a clique, the degrees are all n-1, here the degrees are d, then if you have failure probability p, then what matters here, as we agreed, is the p times d, that's the expected number of neighbors a node has, and the same sort of cutoff that I'm going to use, p times d is 1 plus x for some fixed constant x, that the expected number of neighbors on degree d is a little bit above 1, then I claim you, with constant probability, you're going to form a live edge component that's proportional to your degree. Actually, probably maybe even bigger, but I claim at least proportional to degree. So for example, if the graph is complete, then d is essentially n, and this is the result we had up. But this carries on every other graph. So what does this mean for us, and why is this going to be useful for us? It's because if you have some degree with some probability, you're going to fail, then you're going to have the high enough degree to compensate the people for this failure. They're going to have to benefit big enough to carry the failure, to survive the failure. So every node has a, we'll have, like this will control what the degrees of the nodes are. And in particular, I guess you can, I'll maybe show in a second, can derive that that you can't have degree much bigger than a over p. So if every node has, okay, I promised up front that this is a maximum payoff you can have. This 1 plus a little bit times a over p. Suppose you wanted to have bigger payoff than this. That means you have to have a degree bigger, like every edge gives you a benefit of a. You're going to have at least 1 plus f of delta over p, that is of the form 1 plus x over p in degree. That's how you get that much benefit, even ignoring that there's some negative subtraction from it. But with that much degree, this will tell you that the probability that you're being in a component of roughly your size or constant times your size of the degree is a constant probability. So you're being exposed to a lot of danger. And with f of delta being big enough, that turns out to be bigger than your benefit and your host. So no network can do this. Now I'm only left with 1 minute, but I guess this is sort of the main technical tool here, and let me tell you how we use it. I guess what CARP's proof originally of this of the fact that there is a large giant component was a simple proof thinking about breadth first search. So what does breadth first search do? Breadth first search starts with node A, and I'm going to do breadth first search now on the live component of A, but now I'm flipping the live edges one at a time as I expose them in breadth first search. So first I think, okay, A, what are the live component of A? Which of A's neighbors are live? So I'm going to look at A's neighbors. In expectation, A has 1 plus x neighbors. Okay, 1 plus x over delta degrees, so over p degrees, so in expectation 1 plus x neighbors. X is above 1, so probably more than 1 extra neighbor. I'm going to then have these neighbors put on a queue and take one of the points of the queue and put its neighbors on the queue. Again, in expectation, it has 1 over p, has 1 plus p neighbors. So this system, if you think about, can you think about as a breadth first search making submitting this queue is like a biased random walk with a positive drift. Every iteration, you take one node off the queue, and you put 1 plus x nodes on the queue in expectation. So you're putting a little bit more on than off. This works okay till you're exploring new nodes. At some point, you're not exploring new nodes anymore because you reach back in the network, and that's where the degree comes in. So up to the initial phase of the graph, you're exploring new edges, and at that point, there's a positive drift. In the Clark version, there was a positive drift all the way. Here, there isn't. Okay, and then finally, let me summarize what we get with this technique. So if you allow clustering, you allow naming the neighbors, then we actually can strictly go above this sort of threshold. And in fact, for depending on delta, I can have each node have a supercritical payoff that is a little bit above this A over P, A plus f of delta over P. It depends on delta. As delta goes to 0, it goes to 0 also. But for fixed delta, I get strictly above this A over P payoff. In contrast, if you don't allow people to cluster and have to form link randomly, you can't actually do that. And every graph will have no worse than the A over P that actually, the A over P without the delta addition. You can't have a constant delta addition, but you can have that much. And finally, oh, sorry, that was the answer. That this can have supercritical payoff and those ones cannot. And I skipped the proof ID. And for stable graphs, I guess it turns out that, and maybe not too surprisingly, though the degree is quite surprisingly bad, that the optimal graphs are not stable. What's happening here is that an edge, to forming an edge, confers the benefit of A of two of its neighbors, but it exposes a lot of the other guys to risk, not only the two neighbors that are formed. So there's a strong negative externality. People form too large cliques. If you make the cliques a little bit bigger, then it is stable. It's just too big. At that point, they eat up all the benefit. And the main theorem is that that every welfare stable graph, whatever the structure is, has no bigger benefit than going like a small function going to 0 times A over P that is exponential or arbitrarily smaller than the benefit was from the optimal network. And I had the proof here, but that was too optimistic. And I guess so I told you about the model, which is the opposite of the standard network formation, where being connected to people is bad. It has direct benefit, but exposes you to risk rather than the traditional thing backwards. There are a lot of interesting questions, even in this very basic model. I suspect that every stable network is very clique-like, but we can't actually prove this. I don't know if every optimal network is clique-like. I can't prove that either. So these are the immediate questions. And then there are the questions that Michael nicely asked me in the beginning. This is a very uniform, very simple model in which every edge is equally contagious and equally beneficial. I can't form a more beneficial relation with Nati and therefore maybe more expose myself to risk, which would be a very natural extension, I think very interesting. But that's all we have at this point. And thank you for your interest.